Okay, let's get it started. Don't forget to do attendance. Am I too loud? Okay, 1988, the magical passcode. I always use that.
I did not think I was making it.
I'm kidding.
I thought there was no chance.
Okay, good. Let's get it started. We are still in probabilistic world, and we want to simulate this uncertain world. What we need some math. We call that probability. And for this math, we need some variables. We call them random variables. We are still in random variables. Okay, but continuous random variables. We started last week. Okay, quiet, please. Okay, quiet, please.
She said, I don't even think you have it. Did you?
Okay, 1988, don't forget. So we talked about continuous random variable. So anybody from this area that is, they're talking too much, knows what is random variable? You know?
Yeah, I know.
Okay, what's that?
We define a probability math function to, or it's a variable that can take on the set of values probability math.
Yes, but random variable is very before probability mass function. It's good, but it's not precise. Any other idea? What is random variable? You know that? Yes. It's a variable that is random, isn't it? Yeah? Okay, no. Any other idea? What is random variable? You don't know what is random variable. Random variable, you know. Do you know what is random variable? No? Really? What is random variable? You. What is random variable?
I have no idea.
Really?
Dice roll, isn't it?
Yeah, but what is the definition of? Okay, so yeah, let's go for dice rolling. What is random variable in dice rolling? What? That's random events. What is random variable? It's related. Assigning something to that. Assigning a number to that. So random variable is a function that assigning a number to random outcome. So we are trying to make probability like math. That's the idea, remember? And random variable is a kind of function that transforms these random outcomes to a number. That's called random variable. We call like x, y, whatever, and we assign a number to that. That becomes random variable, okay? And random variable, we have different type, discrete and continuous. Discrete random variables are countable, 1, 2, 3, and continuous, not countable. So like, for example, rolling a die makes some discrete random variables. That this random variable can be, for example, 1 to 6. But for example, if you are measuring the height of people, that's not discrete. This is continuous because it can be anything. It depends how precise you are measuring. Okay, so we know that. I think I know you. You didn't know that properly. So you need to study when you come to the class. You need to at least take a look at what we had before a little bit, okay? At this very, top, like general idea that are important. Anyway, that's random variable. We started continuous one last week, and we want to still keep going, kind of build on that foundation that we made last few weeks, and go further. And the idea is to kind of simulate the probabilistic vault. And these variables help us to do that. Okay, so we're going to talk about PDF again. This started last week. What is probability density function? Probability density function is like probability mass function, but in a continuous way. It's not very similar, but some stuff similar. And also we want to talk about the moments. Any idea what was moment? You remember? What was the moment? I know.
I probably know, but I just don't know the word. I probably know it under a different word.
Yes, moments in probability, of course. What was the moment? They explain 2 moments, 2 degrees. Moments 1 and 2. Yeah, mean and variance. Moments in probability is not that moment that you are there. You're living in the moment, of course. But this moment is for probability, that we have 2 moments, mean or expected value and variance, that's showing how we are varying around the mean, how we are spreading around the mean, how much we have uncertainty around the mean. So this is, when we call moments in probability, it's these 2 right now. We have more, but these 2 are more important. We're going to talk about them. Today, let's get started. Let's go to last week. We said we have probability cumulative distributed function. Do you remember? We call that capital F of x, cumulative distributed function. Distributed function. Okay. Let's see if I can put my screen in a way to can easier write on it. Yeah, okay, good. Sorry, okay. So this is cumulative distributed function. So we said instead of just talking with random variables, we can talk about cumulative random variable. It means probability of x is smaller or equal to a value, like a capital X. We can measure this using probability mass function. We say, okay, if we add up probability mass function is P. P of x for all x in sample space, okay, not for all, of course, for x is less than that value, x is smaller or equal to x. So this becomes cumulative. So it's like summing all probabilities till that x. Okay, so we explained this. Why we want to talk about that? Because sometimes finding probability in one specific point is not easy, but we can always find cumulative distribution or distributed function. We always can find, because it's all sum, is easy to make it. So This was something that we explained last class. But for continuous random variable, we mentioned that for one specific point, we can't find actually probability if this is continuous. Remember, we had the example of this spinning pointer. So we had, OK, so to explain what is continuous random variables, we had this example of a spinning pointer. So we said, OK, imagine we have a spinning pointer. They have different numbers. And this is the pointer here that we are spinning that randomly. And this area is 1 meter. OK? So we had this example last class, how we go from discrete to continuous. So in discrete case, if we turn that randomly, the probability of this arrow staying in one of these from 1 to n is 1 over n, isn't it? If we randomly turn that, it's going to stay in one of these parts that if there is n, we have equal probabilities, 1 over n. Probability of staying 2 is 1 over n. Probability in 3 is 1 over n. All of them. Yes?
The slides, they're like kind of cut.
What? That?
No, we have them, but they're like
Different size?
you can't see the whole slide.
Really? Everybody like that? Oh. How this happened? Wait a second. OK. I can. Go check it out. Wait a second. Do it very fast. OK. Go to here. Go to module. Go to slides. But I see them right here. I think it's just your. Why I see them properly here? I didn't change anything. But I can upload again. But anybody else has this problem to not see this properly? You always, OK, so I'm going to do that. Then, yeah, OK, so I don't know why my computer working, but I can make the PDF again and do that. Actually, that's a not bad idea. I'm just going to discard this, make the PDF again, save as a PDF. Maybe I didn't put proper. OK, save that. Would you like to convert? No. And then again, go back here and go back. Move that slide. OK. Move slide. Add again properly. OK, file. Put the notes. Notes and slides.
That's good. Application value. Standard. And it's also, well, like you put it in.
OK, I did that. Can you check it again, please? To see if everything OK. That's interesting.
It's unsupported item now.
What?
Browser.
It's probably need a little time to update.
You said.
But it's okay? Good. Thank you. Perfect. So let's go. OK, so we were here. We were explaining how we are moving from discrete random variable to continuous. OK, so we are doing a spinning pointer example. So in a spinning pointer example, we said if there is a spinning wheel in gambling, I don't know, probably not in gambling, like sometimes when you want to select something random, you can use that. Anyway, there is different actually segment 1, 2, 3 to n. So probability is 1 over n, as I explained, to stay in one of these. This is obvious. But if the n going to infinity, so OK, probability of x is equal to 2 is 1 over n. And if n is, for example, 10, if n is equal to 10, this is going to be 1 over 10. OK, obvious. What about if n is going to infinity? If become more and more and more. If n goes to infinity, the probability of p equal to x, any x, is 1 over n, going to infinity. That is equal to 0. That's the point. In continuous random variables, we can have probability of x is equal to a certain value. It's always 0. And this is the proof for that. Anytime we want to prove it, you can remember this spinning machine or a spinning pointer experiment, and remember that. OK, so we explained that. But how we can explain this random variable? How we can find something like a probability, like mass function for continuous? We want to define something similar to probability mass function. We call it probability density function that is derivative of cumulative distribution. Because cumulative is add them up. If we get differentiation, is like a negate of summation. So, and because always cumulative distribution exists, when I'm saying always exists, it means for any type of random variables, we have cumulative distribution. We have capital F, OK? So we just can get differentiation. And the function that's coming out, we call it PDF, probability density function. So to study continuous random variables, we can work with this function, probability density function. Why is density? Because is not certain in a point, is in an area around that point. OK, so we're going to talk about that now. But derivative, we know always, derivative is kind of a slope of cumulative or CDF in that point. You know, when you have CDF, like cumulative is like this, for example. In continuous, do you remember? It was increasing. So if this is x, this is CDF. CDF is add up, OK? And the maximum is what? Maximum of this function is what? What? 1. Because when we add them up, it's always going to add up to 1. So the maximum is 1. That's perfect. So, but we are defining PDF, sorry, this is PDF. We're defining PDF as a, something like that. If here is x, for example, and here is d of x. This part, this is a slope, and we are defining probability because even though we don't have probability of exact x, but we have probability of x between like x and d of x, x plus d of x. So this is approximately f of x, d of x. So this slope that is coming from derivative can be explained like this. It's going to be like this area. Why this area? Because we are multiplying the size of that, that is d of x, in the height, that is f of x, and become actually like the area of that, okay? So this is called probability density function. But we don't need to know exactly the math behind it, but we can use them a lot. So anyway, this is showing this like a slope. It's showing this a slope, okay? And if this slope is higher, like a steeper, it means the probability is higher. Probability to be in that interval between x and delta, x plus delta x. And if it's flat, it means lower probability. So if it's flat like that, it's lower probability. If it's higher, it means higher probability. Okay, so that's the definition of that. What else we can say about PDF? Okay, what else we can say about it? So important part is not a probability. So this is important. It's not a probability. F of x is not a probability. This is important. If it's not probability, it can be even larger than 1. So let's draw one example of f of x to show you how this is, how it can be more than 1. So the point is, if it's more than 1, you can have part of that lower than 1 when we add them, because when we add them up, need to be 1. When we add them from minus infinity to infinity, this need to be 1. But how this can be larger than 1, if the part of that is lower than 0, when we add them up, it can be 1. We can see this probability, this property later too. But the probability coming from the actually area under the curve. So the probability coming from area under that, okay? Okay, we're going to see that how. So for any continuous random variable, we have probability density function is always positive. Okay, so this area is always positive because this area can be negative because when we add them up. And this is always 1 when we get differentiation from minus infinity to infinity is always 1. And when we get derivative of that, because when we get integral of that, we're going to back to cumulative actually distributed function. So the relationship between cumulative distribution function and probability density function is integral and differentiation. So because differentiation is against of or negate of actually integral. So we can do that. So this relationship between CDF and PDF. And as I said, CDF exists for any variables, for random, any, yeah.
What would be a physical example where the probability distribution function is negative?
Any example of that? Probability density function be negative?
Yeah.
So it's not be negative, it's always positive.
Okay, because you were saying that when we integrate it, it can be larger than 1, it could theoretically be negative.
Yes, so I think that's, it can be larger than 1. So when we, okay, so the area is the CDF, okay? Okay, this is for CDF. Let's see how, oh no, sorry. Yeah, that's a questionable. I don't know. I think I'm gonna check this. I think something fishy. You're right. I think I made mistake. Maybe this is not right. I'm gonna check this point. If how this can be larger than 1, I don't know right now. Yeah, I will check it out. Thank you for asking. Actually, I got that. So, how this happen? How this can be more than 1? But I'm going to check that and come back to you later. Very, very good. Very good point. Sorry, I think I made something wrong. Maybe that's not right. I'm going to check that. It can be larger than 1. How this can be larger than 1 when is always bigger than 0, but we add them up. OK, so let's see how this is happening. So we add them up. It becomes 1. How this can be, how we can have them always bigger than 1 and this be bigger than 1. That's something, I think that's not right. But I'm going to check that because I wrote that from the book. I think something, I didn't think that time, but right now that, when I draw that and I said, oh, this not make sense when you ask, yeah.
Something weird like a Dirac delta?
Direct delta is when you want to move from, continuous to discrete. We can use that. But I'm gonna come back to you next class, the next time, and explain that. Yeah, that's fishy. That's how this can be larger than 1 and sum to 1. Yeah, that's good question. I don't know really. I wrote that, but I didn't think about that time. But I'm gonna think about that soon. Yes, what's that?
Example of the CDFs.
Yes.
Of the derivative being greater than 1 is a discrete CDF.
Yes, this is CDF. Yes.
So that right there, the derivative would be basically infinity, right?
Yeah, we don't have derivative in that point. Yes. We don't have derivative when we go there. Yes, you're right. Yes. But CDF is always exist, but PDF not always exist. That's a good question. Yes. Another question was you asked me?
Is f of x the slope?
This derivative is a slope in CDF. When you get the slope in CDF, yes, the derivative is always a slope.
So is that what it's saying can be larger than 1? I mean, that, if it's the derivative that can be larger than 1, then that makes sense because it can just be over.
Yeah, so I think about that, but I don't know really why these two at the same time can happen. Yeah, might be. Can we have that angle higher than 1? So yeah, it's lots of things behind it. I can think about it. Next time I'm gonna come back. Yeah, this is good. Always, let's tell you something. You don't need to know everything. If you don't know something, you can go search and find it out. So this is good point of being an engineer. You need to accept sometimes there is some fishy stuff here. We need to go figure it out. But I'm gonna go check it out and let you know. That's actually a good point. How these two at the same time can happen, and that's be true too. That's something interesting that I'm gonna check how this can happen. So because if the sum is 1, a part of this need to be under 0, and how this can be always bigger than 1. And one of these two are not true, that or this. But the reasons that you mentioned all make sense, but I'm going to check it out for next time. OK, so that's good. That's good point. So we got lots of things. with this talking, actually. So regarding to PDF, how we get PDF derivative, how we get CDF from PDF, we get integral. They are against each other. So, okay, let's go to probability of interval. So probability of interval for a random variable is also exist. You just need to get integral in that interval. That makes sense. So for example, if CDF is a function like this, okay? So if you want to find probability of x is between a and b, you just need to find the integral. And integral is actually area under PDF, under CDF, and but this probability is this is sorry, this is PDF, not CDF. PDF, probability density function. So the area under this is so it's not going. I messed it up with. So it need to come down because we can't have infinite. It need to add up to 1. So the probability of x between a and b is the integral of f of x between a and b. That is this area. So this means probability, even though for one specific point is not exist, for an interval is exist. And that is the area under that curve. Okay, so this is probability of interval. Let's have one example. Let's go for uniform distribution. Here we're going to see continuous form of uniform distribution. Let's clean this up. Do you remember what was uniform distribution? So uniform distribution was like a kind of distribution, like that a spinning example. So in that a spinning pointer, so a spinning pointer was like that. Your probability is equal for all of them. So the probability of any outcomes are equal. So they are all 1 over n. And when n goes to infinity, that becomes continuous. Okay, but this x, this is x. X is this area. X is this area, and x is between 0 and 1. Why? Because we consider this area maximum 1, from 0 to 1. So, and this x be in area 1, in area 2, in area n, the probability is 1 over n, but when it goes to infinity, this becomes continuous. Okay, so what I ask here, we have this uniform distribution. So why is uniform? Why is uniform? I ask you again. Why distribution of x between 0 and 1, that here is between 0 and 1, is uniform? Yes?
Each slice has an equal part, equal proportion.
Equal probability to be in that portion too. Yes. Is equally likely to be in any of those. And I wrote that 1 over n. So that means it's uniform distribution. Rolling a die is the same. In rolling a die, probability of being 1 is equal to probability of being 2 to probability of being c. What is that probability? Yeah, 1 over 6, exactly. This is probability of x is equal to x. So this is probability mass function. So, but here we have like this is not continuous. But what about that? let's draw this one. In this case, this is going to be continuous. So we are saying this is f of x. This is probability mass function. This is probability density function. We want to see how they are close to each other. We are between 0 and 1. The probability is 1. And the rest is 0. It's kind of like this, but it's continuous form. Continuous form might mean between this and this, but this continuous part are all equal because it's uniform. Can we say what is probability of, for example, x is equal to half meters, for example? Can we find this? What is this? Probability of x is equal to half. Like you are doing this, spinning this arrow, what is the probability that it stay exactly in half? 0, yeah? We prove that this is not possible because it's continuous. So here we can't find this probability because it's very little. But we can always find the interval between something. OK, let's see what we ask here. Here we also ask about interval. I need to clean this up. Any question about this? This is showing how we are moving from probability mass function for a uniform discrete form to the continuous uniform. So uniform has two type of variables: continuous form, that is this, and discrete form, like rolling a die, same. But this is going or coming from this spinning experiment. Okay, no question? Okay, let's go for, I need to clean this up. That's why I asked you if you have a question. Okay, what we want to find? Interval. We want to find what is the probability that x be equal to between 1/4 to 3/4. I'm going to ask you one question. Is this different than probability of x between or equal 1/4 or not equal, for example, 3/4? I'm saying, are these two equal? We add this part equal and not and remove this equality from that side.
Yes, because it's whether or not you include it, the probability of a given number is 0. So it doesn't matter whether you
exactly. So they are equal. So yeah, they are equal. So it doesn't matter. If I forget to put this, is equal because probability of being exact number is always 0. So these two are equal. These two are equal. Okay, this was the one point that I wanted to mention. Okay, so let's clean this up. So how we can find this? We can compute this integral. This is the PDF. So between 0 and 1 is 1, or otherwise is 0. When we get integral, in this portion is coming from that. F of x is 1, and the integral between that is going to be 3.4 minus 1/4, that is 1/2. So this is coming. This is a normal integral, okay? So the visualization is actually like that. So in this visualization, as you can see, this is between 0 and 1. That's a PDF. F of x is 1. When you multiply 1 by 1, the overall area is always 1. But we want this portion. We want between a and b are 3/4 and 1/4. So we find this area that is half. That's any question about that? So in this example, you can see continuous form of uniform distribution, and that's important. Continuous form of uniform distribution. Uniform distribution, how can be continuous? Yeah, like that, it can be. Why? Because still you can multiply them and it become 1. Like that example of rolling a die, when we add 1, 6, 1, 6, 1, 6, 6 times, it becomes 1. Here you are adding 2 because integral is like of addition. Integral is like of addition that give you the area under the curve. Okay, here we have just line, not curve, but same way. Okay, so let's do example of another not uniform. Let's consider voltage. So we have voltage for, in digital logic, for example, you want to design a circuit and you want to have 0 and 1. Like computer, and computer using voltage to show 0 and 1. For example, -5 for 0 and +5 for 1. So x as a random variable is the voltage. And this voltage is changing from -5 to 5. So if you want to draw PDF for that, probability density function, and this is x, x is changing, for example, from something like -5, and here is, for example, -10, -5, and then going to 0, and then go to 5, and more. And we want to see what we are saying. We say, okay, this probability density function is, for example, 0 and going to, for 5, -5, this is like going like that, and going for 5 is also going like that, is like that. This is probability density function, okay, for the voltage. So that's showing 0 and 1, for example, okay? So this is the voltage form. Let's see what we can say about that. Probability graph visually shows likely values. Okay, first of all, probability of x is equal to 1 point is 0, because we can have that like normal continuous random variables. But we always can have this. We can say probability between 1/4 to 3/4. Like, I don't know if it's exactly in that area. We can find this area. We can compute that. So this is a kind of continuous form for probability mass function and for voltage. Okay? So this was one example. So endpoints not matters. As you can see here, I mentioned this is exactly equal to this because it's continuous probability of exactly be 1/4 is 0. Okay, so that was, okay, that's another picture of that. So as you can see, the total PDF is actually 1. A probability density function around the 5, for example, -5 is for 0, and +5 is for 1. Okay, let's do another example. This is a function that we're going to see that later a lot, is a variation of decaying function. Do you remember last class? Or, I don't know, maybe last week, I explained a function with this form and said this function is a decay function. Decay function, you're going to see that a lot in different applications. Let I clean this up. This is another function, the variation of that, when we have an x here, and then exponential minus x. This minus is very important part. This is called gamma function. This gamma function has lots of applications. It has a story, but I'm not going to tell you. But anyway, this is gamma function. Gamma function has very great shape, is like this, and going, it has a going to infinity. It starts from 0. Is a start from 0, going rise to a peak, and then get skewed to the right side. This function is very good function. It's like a normal function, but it has a skewed. So many applications can model using this function. Like, for example, imagine you are measuring trust. You want to see how you trust your friend, okay? Sometimes, okay, maybe trust is, that's fine. Yeah, actually, trust is good. So you can say, okay, trust start, I make it reverse. Trust start, because negate of that going to go that side. Anyway, trust start slowly, get to the higher, but you lose trust very fast. So it means it's not symmetric. This is a function that you can use for modeling this type of phenomenon that is not symmetric. You have some skewing part, negative or positive. This is for positive, but we can use it for negative too. So the negative part starts from here, going to the maximum, and then lose very fast. Trust is happening like that. Like getting trust is so hard. Little by little, you need to see, for example, between human, it takes a long time to get trust. And with very little things that you do, you're going to destroy it all. So it's going to go down very fast. So many phenomena are like that, actually. OK, so that's why this function is important in that case. What we ask, find the C. We have a constant C here. We want to find it. How we can find it? Any idea? Yes?
You can integrate it, set it equal to 1, and then solve it.
Perfect. Exactly. So you need to, because we know the integral of PDF is 1. So we need to get integral and equal it, put it 1, and then find x. So how we can do that? So let's see how we can find that one. OK, we find integral of, because it's x is bigger than 0. The rest is 0. We just need to get integral from 0 to infinity. And get this integral cx e minus x over 2. D of x is equal to 1. So the integral of this c is a constant, can go out. So you can bring c out easy. OK, so the point is we need to compute this integral. But this integral is a very well-known integral. So how we can compute that, you need to use this, what is it called? Integral by part. You need to consider that 2 part and compute that. But do you know that? Do you know how to compute integral? You know that, yeah, of course. You know that. And anybody else, you know everything. Anybody else knows how to compute integral? Yeah, you know. Yeah, of course you know. How? Anybody can compute this integral? Huh? You need to get u and v. Remember, 2 parts? That's the trick. You need to get u, and I'm just going to go explain that part, and I'm not going to go all of it. I don't have time for that. But we get u is equal to this part u, and this part d of v. Remember? It's just changing variable. It's called integration by parts. By parts, okay? So u is x, so d of u is d of x, okay? This is one part. D of v is e minus minus x two, okay, d of x. So v is 1/4 e minus x 2. Is that correct? Anyway, if it's not, this is the method that we can use. And then you can use this formula. You have a u d of v is equal to uv minus v d of x. So this is the formula that's used for integration by parts. So you need to use this method in after doing that and substitution and using those, c, you can find c that is 1/4. Okay, do it at home. And if it's something not clear, let me know next time. Okay? But getting integral is not part of our class. I'm not going to ask you in exam to compute integral. Yeah, if I want to, I'm going to give you all of the details you need. Yes?
Is this gamma distribution related to like the gamma function that's like the analytic continuation of the factorial?
Yes, it's related to factorial. Yes, exactly. Very good point. Yeah. Actually, the history behind that was for I don't remember the name of him, but he was working in factorial. He was working to factorial and came to, because this e over minus x is going to factorial. They wanted to measure the factorial series. Yes, thank you. Very good question.
It doesn't really look a lot like the gamma function.
Sorry, what?
It doesn't really, like when you draw it out, like I'm used to the gamma function not looking, not like a pulse like that. It just shoots off like the factorial.
Oh, yes.
I'm a bit confused at kind of how.
Yes. Yeah.
Is this just like entirely unrelated and has a similar name, or is it?
The gamma function is different, you know, but this is this PDF is also coming like that. You are saying gamma function is actually this one. Is a gamma alpha 0 to infinity. I have it here. T is just change of variables. Alpha minus 1, e minus t, d of t. And as you mentioned, it calculated to measure something about factorial. We don't need to know all the history behind it. But this function is very similar to that. But you're asking how the function can be like that, yes? The function is like that, actually is a part of question. The second part, we want to see how this function is going to look like. Let's see how. Okay, that's actually tricky, but let's see if we can explain it properly. Let's clean this up. This is the second part, how the function is like that. What I am saying, the function is like this. First of all, in 0 is 0. Do you agree with me? Like this is f of x, PDF. And this is x. When x is 0, the function is 0 because we have a x. So it's 0. What is the maximum of this? To find the maximum, you can get derivative. So you can get derivative of that and put it equal to, okay, derivative of that, we know x is 1/4. So let's just get derivative of if g of x is x e minus x over 2. Derivative of that, g of x prime, is e minus x2 plus x 1 minus 2e minus x2, okay? And we need to put that equal to 0. If we put that equal to 0, we can find x. X is going to be 2. So it means in 2, this is a maximum. So this is a maximum in 2, and then get lower, like that. So to draw that, you need to find some points and connect them together. But when you find the maximum, this is, but this is because it's very famous function, is showing the rest is skewed when we go to infinity. And this skewed angle is exponential. It's going exponential. But the maximum is important. The maximum is 2. That's the gamma function. But this is the gamma function is like that. It's not increasing forever. Okay. So but finding the maximum is important part. Finding the maximum part or the peak part is important, that we can use it with derivative. You know, a derivative always showing the maximum of a function. Okay? Why? Because derivative showing the angle. When the angle becomes 1, becomes 0, it means become flat, so that's a maximum. However, if the function is increasing function, okay, we can use that. But if there is coming down and again go up, maybe that maximum is a local maximum, but is not global maximum. That's for another topics, and it's not related to this now. Is optimization. Let's clean this up. But the gamma function is like that. To skew that, you just need to have 2 points, this point and that point. We don't need to find exact, but you can find another one, like 4, and compute that and see what does that look like. It's going to be something around, for example, I don't know, a number over there. And I actually draw that in a better version, so let's show you that one. I use a programming for that. So, for example, the maximum is 0.17 as a PDF. So, for example, if you find in point 10, if you put 10 instead of x and instead of C1 over 4, you can compute that and connect these points together to draw this PDF. Okay, what is the last part? The last part is computing CDF. So the CDF is actually integral of PDF. So we have PDF now because we computed C. So we can say CDF, that is capital F of x, is equal to integral 0 to x 1 over 4 t, not t, x, e 2 d of x. You don't need to compute it. Yeah, just write it. That is okay. Okay, that was one example how we are dealing with CDF and PDF and sketch PDF and how we can find some constant like that. You might have something like that for your assignment as well. Any question about this? This was just relationship between CDF and PDF for some continuous random variables. So let's go for expected value. So we know expected value is like mean, is like weighted sum of that variable. So weighted sum in continuous become weighted integral. Yeah? Do you remember expected value was weighted sum of x? This weighted sum in actually discrete form become p of P of x. So we knew that, and x is belong to, that was expected value in a discrete form. So this was in discrete form. What is the weight? This is the weight. This is the weighted. That's why we call it weighted sum of x. We add x. We weighted x and add them together, and that become mean. Okay? So this was for discrete form. For continuous form, sum changed to integral, and probability mass function goes to probability density function. That's it. So it makes expected value. Okay? If instead of going to infinity and minus infinity, we just go between a and b, and the rest be 0, still we're going to have a same situation. Okay? So here I explain that is similar to the discrete form. And in discrete form, why we can't use just sum? Because in continuous form, probability of x is a given value is always 0. But in here, you can find it as an integral, that is the area behind the curve. Okay? Yeah, integral is a continuous version of summation, of course. And intuition is that thinks of PDF as a weight. So this PDF as a weight, as I mentioned, and x is just the random variable that you are weighting that random variable and get average. Okay, let's do this example for this iClicker. Okay, I need to, for defining variance. I want to see if you remember variance. iClicker, I need to start it. Give me a second. Probability, start class, and the pool, start. Okay, select. Okay, do you remember what was variance? In this example, I'm asking for a continuous random variable x with mean mu, which is the following correct definition of variance. Because variance showing how you are varying around mean, how you are spreading around mean, how you are changing around mean. If the mean is here, how you are changing around it. Okay? We said we can compute that with distance, remember? Okay, so which one is the correct? Let's see what is your answers. So mostly people saying B. Some people saying A. A is also distance, but because we want to make it positive, we make it a square of distance. So what about C and D? C and D is just a square, but we also, so the correct answer is B, actually. Most of you guys did good. But this is also equal to expected value of x squared minus a square of expected value of x. This is equal to that. We computed that later, before. You know that. Anyway, most of people did good. Thank you. So I just wanted to remind you that what is the definition of derivative. So derivative is showing how you are spreading around mean. So how you do that, you just need to measure distance around the mean. This picture, you can see this is the mean. This is the mean, mu. And this distance is x minus mu squared. But you get mean of that. So this E is another mean. You add them up. and get the mean. So this becomes that. Okay, good. And class, that's done. Any question about this before going to this part? Let's see how we can find variance. Variance, because variance is expected value of this distance square. So easily, if you have expected value, you just can find variance easily. Imagine the expected value is mu. So if you compute the formula that already explained, doesn't matter if x is continuous or discrete. Variance is always this. So the difference between continuous and discrete is coming to computing expected value and expected value of a square of x. So you need to compute these two. How we compute them? We already know how to compute expected value of x. Expected value of x was integral minus infinity to infinity x f of x, d of x. And for a square is exactly a square. That's it. So example for the uniform distribution. For uniform distribution, we can compute that. Okay, what is the expected value for uniform distribution? If you remember, uniform distribution was this, f of x, 1 if x is between 0 and 1, and 0 otherwise. Okay? So let's get E of x. E of x is equal to integral minus infinity to infinity x, f of x, d of x, and this is between 0 and 1. F of x between 0 and 1 is x. D of x, that is equal to x2, 2, 1, 0, and is 1 over 2. Good? It's just formula. The integral, and then we have the function, is a 1 function. So x1 is x. Integral of x is x squared over 2. This over 1 over 2 coming from here. How we find E of x squared, we do the same. But integral of x squared is x3. 3. When we put bands around it, it's going to be 1 over 3. And 1 over 3 minus 1 over 2 squared is 1 over 12. So that's the final answer for variance. That was easy. I mean, the integral was easy because the uniform is very, very simple, actually, distribution. Let's do the last part of the class and finish it up. What about if instead of x, we have x squared? We have g of x in general, another function that we want to find expected value of that. We know x, but we know x. X is a random variable, and we know PDF of x. This is PDF of x. But what about expected value of x squared, for example? Expected value of x squared, or expected value of 3x plus 5. We have enough information about x, but do we have enough information about x squared? I want to mention that, yes, in this case, we can actually use the formula, even though we have information just about x, but we can get some information about expected value of g of x. How? Same way, instead of x, we just put g of x. expected value of g of x is again the integral. We don't need to know PDF of g of x. We just need to know PDF of x. PDF of x. Okay, let's do example. This is the same thing that I mentioned. Let's do that for this linear function. Imagine g of x is ax plus b. Okay, so expected value of ax plus b, that is g of x, is this g of x multiplied by PDF of x. So, and because this is linear function, integral can distribute in that function easily. And another point that we know, this integral is e of x, and this integral is 1, so it's going to be equal to this. So this is how expected value can distribute in a linear function. But that was one example how expected value is actually interesting. You can get expected value of the function without knowing the PDF of that function. You just need to know the PDF of that variable of function. Perfect. So that was for today. Next class, we're going to see other families of continuous form, specifically random variable, specifically normal random variables, or Gaussian random variables. That is actually very important for our class and projects and everything. Okay, have a good day. If you have any questions, let me know.
Almost like 20 minutes ago.
I don't